Here we have the graph of y equals x squared, and we're looking at the graph. What do we mean? How would we graph y equals ax squared? Well, that depends on what a is. For example, here we've graphed y equals 1/2 x squared. Okay, now the graph of y equals x squared, when x is 1, x squared is 1, so y would be 1. When x is 2, the square of 2 would be 4, so y would be 4. So you should understand, of course, how these points are located. Now if we do y equals 1/2 x squared, then every value on this graph will be half as great as every value as the corresponding value on this graph. So when x is 1, where this graph has a value of 1, this one will have a value of 1/2. And this graph is going to be half as high as the other. At every point, the graph of y equals 1/2 x squared will be half as high as the graph of x squared, where height is measured from the x-axis up to the graph. So that when x is 2 and this graph is 4 units high, this graph will be only 2 units high. At every point, that's the case. Now we can also look at the graph of y equals -2x squared. That's, of course, the graph that you see here. If we multiply x squared by -2, we get a value that's twice as large but negative. So if x is 1, we're going to get, when we multiply by -2, we're going to get -2. If x is 4, we multiply by -2, we get -8. So what happens is every point on this graph is twice as far from the x-axis as the points on the basic y equals x squared graph, but in the negative direction. So twice as far from the x-axis on any vertical line and negative. Now this vertical line thing you see here and here just means a vertical line, for example, goes through x equals 1. Anywhere on that vertical line, wherever this graph is on the vertical line, this graph will be half as far from the x-axis on that vertical line. This will be twice as far, but in the opposite direction. We can also look at this in terms of vectors, which are just represented by arrows. Okay, if we take this point on the graph, the vector from the x-axis up to this graph is only half as long as the vector from the x-axis up to this graph. Both of these vectors, this one and this one, are considered to be drawn from the negative x-axis. On the other hand, the vector that goes to the -2x squared function is twice as long as the one that goes to the y equals x squared function, but in the negative direction. Another way of looking at where this vertical stretching comes from is from the table. Okay, if x takes values -2, -1, 0, 1, 2, then x squared will have these values, as you can easily verify, so that 1/2 x squared will have half of each of these values. That again makes it twice as close to the x-axis. 2x squared, of course, has double each of these values, making it twice as far from the x-axis. So we see that this vertical stretching idea, where, for example, this graph is stretched by a factor of 2 relative to this graph. Take the top graph and stretch it out twice as long, and then turn it upside down, and we have this graph. This graph is stretched by a factor of 1/2, which actually means it's compressed toward the x-axis.